record this session, and I'll start from the basics of finite element analysis, and also I'll give you some insights about the calculation point of view and what is stress and everything, so that we can get into ANSA. See, there is something called as, from the industrial perspective, something called as design validation. So here we are now going to see what is design validation and how many are ways by which you can validate any design. And then what is analytical method, what is numerical method, what is experimental method. These are the three methods by which you can validate any design. And under numerical method, you have subcategories, which is what we are actually doing for real-time complex industrial problems with the help of computer and softwares like ANSA, ANSYS, Hypermesh. So the numerical methods are as follows: finite element method, boundary element method, finite volume method, finite difference method. Then we'll also see about what is computer-aided engineering and what is the difference between CAD and CAE. Okay. So here is the thing. Design validation means whether the component which we are going to manufacture will sustain for various loading conditions or not. Let's say you have three various fields, right? Like CAD, and the next one is CAM, and the third one is computer aided engineering, CAE, right? So basically CAD means it is computer aided design, but in the name it is actually design, but this is actually called as modeling. Modeling means whatever physical component which you are going to manufacture or design, you are going to produce the same thing using the software, which means you are going to draw using a 3D modeling templates and the tools available in the softwares. Now, after the creation of the 3D modeling, this CAD engineer will send that particular file to computer aided engineering department. This guy, what he does is he will evaluate the output parameters like stresses, strains, or in some cases of applications of temperature, whatever. And these output parameters, if it is within the sustained limit, then he will give the signal to this department. Then this particular computer aided manufacturing will start the production. Suppose if the stress and strains are more than the expected levels or where it should be, and if it is more than that level, then this particular department will again resend the component to the CAD department, and then they'll ask to do some dimensional modification, most probably dimensional modification, so that once after finishing the 3D modeling, once again he will send back to computer aided engineering department. Once again he will evaluate these parameters, and now this time if it sustains, then he will again give the information to computer aided manufacturing to start the production. Now till this it is clear for you? Till this it is clear for you, right?
Yes.
Okay. So design validation means we have to check whether the component which we are going to manufacture will sustain the various loading conditions or not. Loading in the sense not only the application of force, it could be torque, it could be moment, any case. Okay. So in other words, we can say that the design validation is a process to find out the output parameters like stresses, displacement, strains, fatigue life, eigenvalue, heat flux, etc., depending upon the application which we are doing, and which may or may not come on the model, which leads to failure. Ultimately, we are actually doing this to avoid the failure, and then only we can present or start producing and supply it to the client who has given the orders. Now, you might have been familiar with the this experiment, which you might have done using your universal tensile testing machine. Okay. So basically there is a cylindrical rod where it has been subjected to a tensile load of P, axial tensile load, because this load is acting exactly on the axis. Okay. Now because of this load, the rod is now going to elongate, right? Now each time when it elongates, you can notice down that the area of cross section at this junction will keep on decreasing, which is nothing but the necking or neck formation. Now after a particular point, this starts breaking, right? Now, at that point of breaking, they will check what is the stress which is happening. So, stress is basically defined as load acting per unit area, which is nothing but internal resistive force acting per unit area, right? If this stress is well below the yield point stress of the material, you know that each component is made up of a particular material. Let's say, for example, if it is made up of C45 steel, carbon 45 steel, then it might have some yield value of 330 Newton per mm square. Now, if that point where it breaks, if that stress is well below the yield point stress of the material, then it can actually sustain the correct application, and then he or computer data engineering department will give the signal to the computer data manufacturing department to start production. Okay. If not the case, then he'll modify the dimension. Like for example, he might increase the diameter, the cross-sectional diameter, so that it might give some stability. Okay. Or he might take some other necessary action against the modification of geometry, so that sustainability is achieved. Okay. Now, there are three methods to validate any design. One is analytical method, another one is numerical method, and another one is experimental method. So for example, let's take a common thing which you might have studied under mechanics of solids or solid mechanics or strength of materials. In different names, it would have been circulated in different universities. Okay. So let's take a simply supported beam as an example. And let's assume that there is a point load which is acting of value P. And this let the length of the beam be L. And this point load is exactly acting at the middle position, which is L by 2 from both the ends. Okay, now you know that because of this transverse load in the sense it is acting 90 degree to the axis of the beam, because of which the beam is now going to bend. So I can say that the beam is subjected to bending stress, sigma B, bending stress. And this bending stress can be calculated, which you might have studied in your mechanics of solids or strength of materials or solid mechanics under whatever name. So using your bending equation, which is m by I equal to sigma by y equal to E by R. So if you compare the first two terms, this stress is nothing but the bending stress, which you are looking, let me put sigma B. So this bending stress would be now rewritten as my by I, which can be again rewritten as m by I by y, which can be again rewritten as this I by y is nothing but z. Z is nothing but section modulus. This section modulus is a one which actually depends upon the dimension of the beam, cross-sectional dimension, which gives the stability. Okay. So, or I can say that this determines the strength of the section. So if your Z value is more, then I can say that the bending stress is reduced. So which means our ultimate aim is to strengthen this particular component in order to withstand the loading condition which has been subjected to without getting any failure, right? So if the section modulus is being improved, then the bending stress will be reduced. So this is what the computer aided engineering department engineers will try to do. Now, coming to the analytical point of view, you might have found out that the deflection exactly happening at the point where the load is acting is the maximum one. You can call that as Y max or del max, whatever, where this is nothing but deflection maximum. This is also deflection maximum. By any way, you can mention it. Now, that takes an exact expression of PL cube by 48 EI, which you might have studied by deriving, by doing derivation, you might have arrived at this expression, and that derivation might actually go for some 2 to 3 pages. Similarly, your bending stress will also be calculated like M by Z, like what I have mentioned in the previous slide. Now, this is what the analytical method is. Now, coming to the experimental method, experimentally, you will use the universal tensile testing machine to perform this analysis. Okay. Now, where you will actually try to hold the workpiece at one end, and you will try to pull using the other end of the jaw, by which the tensile load is applied on the cylindrical component, and then you will study for the stress and strain, and then you will notice down at where the failure occurs and what is the corresponding stress which is acting. Okay. So this is what generally we'll do in experimental method. But for our case, if you take the simply supported beam also, we'll be able to do it experimentally using the machines whatever we have in the laboratory. Now there is one more method which is called as numerical method. A numerical method is the usage of computer as a hardware, and some softwares like ANSA's hypermesh are available to do the same. Okay. Now we'll notice down what is the advantage, disadvantage of all the three methods. Say analytical method, it gives 100% accurate results. Okay, no doubt in that, because you have been deriving and arriving at an expression. Okay. And disadvantage of the analytical method is it only find the results if you have formulas, right? and it is a time consuming one, because you know that for each and every case you have to derive and arrive at a separate expression or formula. Then accuracy can't be believed blindly, because it depends upon the person who is actually trying to do. And calculations can be done only on the single point. This point I'll explain you. See, for example, you take the normal this case as an example: simply supported beam subjected to a point load. Now you will be able to find out the deflection at this point, but you are also noticing deflection at this point and this point, which you can't actually find out. You can find out, but you have to separately derive for these points. Then only you will arrive at the expression where you can again resubstitute and get back the deflection answer. Which means basically the main drawback of analytical method is you can validate the design only at a particular point. Now coming to the experimental. So experimental has some real-time advantages, because you are considering the physical and manufacturing errors in your results. And it is actually the actual measurement, since you are physically doing that. The disadvantages of the experimental method, it is time consuming and it needs an expensive setup. The cost generally associated with the experimental analysis is actually huge. And it is applicable only if the physical prototype is available, which means you should have manufactured at least 2 to 3 components or 3 to 5 components. Then only you will be able to test that. So then minimum of 3 to 5 prototypes must be tested. Let's say, for example, I'm having an industry, I'm producing some nearly 10,000 parts per day. And if I put it, say 100 in each container, okay, then randomly I'll pick 3 to 5 out of this box and then try to do it. If this is the case which has been followed in the real-time industry, then it will be very difficult to meet out the production demand. Okay, and will not be able to be in a position to deliver the products on time. So this is a huge disadvantage regarding the experimental method. Now, coming to the numerical method advantages, we can solve real-time complicated problems. That's why we are actually doing this. Then the results can be achieved faster, because we are not going to solve, because you know that this has been associated with lot of matrix calculations where we don't need to do anything. We'll just do the coding, and those good persons have already created the software. Our aim is to just use this as a calculator and give the required inputs as per the software is asking. And once if you have given everything without any error, it will immediately, get down the results. Then results can be achieved on the entire geometry. This is contradictory to this particular point, which means using numerical method, you will be able to evaluate the deflection at this point, this point, this point, and every point you'll be able to do in addition to the main point where the load is acting, where the deflection is maximum. So these are all the main advantages of the numerical method. The disadvantage is it gives an approximate result. So approximate result in the sense, say, let's say, for example, for the previous example, I'm getting the analytical solution deflection maximum answer as 0.02 mm. Then for as per numerical method, if you would have done using some software, then the maximum deflection answer would have been something like 0.01999798, something like this, which is numerically equal. So nowadays, a lot of advanced algorithms have been coded in the software to reduce this difference between the actual value and the the value which we have brought using the software. So the difference between the actual value and the value which we have obtained is very much reduced, which means error is very much reduced. So you are able to understand up to this, right?
Yes.
Okay. So if you have any doubts in between, you can ask me. Okay. So coming to the numerical methods, there are 4 total numerical methods available. One is finite element method, or it is otherwise called as finite element analysis. Mostly in most of our Indian standard curriculum, this one subject has been included to give an basic idea of the numerical methods, which has been widely used in the industries. Then you also have something called as boundary element method. Then there is one more thing called finite volume method, and one more thing called finite difference method. See, finite difference method is actually a mathematical technique which has been employed. Okay. So all those numerical mathematical techniques will come under this. Let's say, for example, you know how to find out the roots of the equation, right? For example, x square minus 5x plus 6 equal to 0, which means you might use some formula like minus b plus or minus root of b square minus 4ac by 2a. And this formula is applicable for any equation having of this kind. Now you can compare these two equations and get out your a value. A is your x square coefficient, which is 1 for our case. then B is actually -5, then C is actually 6. If you substitute, you'll be able to find out the roots of the equation. Now, this is fine if you are able to have only power 2, but in the case of engineering, while solving the differential equations, will have higher order, like the powers of x power 4 or x power 6. In that case, you will be able to solve those equations using the numerical technique. One such numerical technique, I think you might be familiar, is Newton-Raphson. Have you read about this?
Yes.
Okay, so these kind of methods have been generally employed in these kind of numerical methods. Okay, and the software which has been belonged to. Now, coming to each and every method in detail. Finite element method means it is actually a numerical technique for finding out the approximate solution to any boundary value problem. For most of the engineering problem, we'll be dealing with the partial differential equations. So it is also referred as finite element analysis. Okay. So let's say, for example, let me take the same example of simply supported beam. Okay. Now let me represent the beam alone like this. Now, instead of taking or considering this entire beam as a single element, they will divide this element into several elements. This is my first element, second, third, fourth, fifth, sixth, seventh. So this is nothing but the finite element method of approach. And what is the meaning of boundary value? Means it is simply supported, right? So which means the beam cannot go in this direction. Okay, certain degrees of freedom has been arrested at both the ends. Okay, so those are nothing but the boundary value things. Say, for example, I can even represent this boundary as at x equal to 0 position, starting position, my deflection is 0 because of the presence of this support. Similarly, this can be redefined using the boundary as x is equal to L position, which is the final position where the deflection is 0. And also, due to the presence of this load, I know that exactly at the point where the point load is acting, the deflection is maximum. So this can also be defined as a boundary condition like x equal to at L by 2 position, I can say my deflection is maximum. So these are all the boundary value things which will be applied for any partial differential equations. That is how it has been solved. Now, basically, what are all the inputs and output parameters generally? I'm not saying that those specified in the slide is only the inputs and outputs which can be done in the finite element method. This has been given as an example for you. You can actually give some inputs as in the form of loads. Loads could be like forces, pressures, velocity, acceleration, temperature, torque, moment, anything. Okay, and also you will give some constraints that this moment has been arrested here, something like that. You will give the constraints, and in certain cases of application, you might also give some temperature as input. And there are few outputs also available. The outputs could be like forces, displacement, stresses, and strains. And note that you can even do some analysis where the inputs and outputs can vary with respect to time. So this is how the normal diagram looks like, normal component. After dividing it to several elements, you can see how many number of small elements are present. Then after doing the analysis, we'll study for the stress distribution or strain distribution, something like this. So now we'll come to the boundary element method, which is a second numerical technique. So whatever you have seen related to finite element method, everything remains common for boundary element method also. The only difference between that is here only surfaces are considered rather than the entire 3D solid geometry is considered. So I can say that it is more and more related to surfaces rather than a 3D part. 3D in the sense three dimensions are comparable. Surfaces in the sense only two dimensions are comparable, and the third dimension, usually thickness, is negligible. So here also the same type of inputs. In addition to that, most of the surface domain where we are trying to analyze using boundary element method will actually take the vibrational parameters into account. And in the outputs also we'll study some vibrational effects. So this is a difference. And we have given an example for that, like car body, for example, car doors, where we'll actually study about the noise, vibration, harshness can also be formed under the boundary element method. Okay. There we also say that the inputs and outputs may vary with respect to time. Like for example, in the case of dynamic analysis, here also you can actually vary your inputs and outputs with respect to the frequency. Then there's one more method called, which is called finite volume method. Okay. So see, instead of dividing the entire geometry into finite elements, here we'll go for finite volume. So basically, this is a thing which you might have followed in your fluid mechanics as a subject and thermodynamics, right? So here unit volume is considered as per the finite volume method, as per the finite volume method. contradictory to the finite element method where we'll consider only the elements. Okay. Now here the entire analysis actually is based upon these three equations: law of conservation of mass, law of conservation of momentum, and law of conservation of energy. And you know that all this finite volume method is completely based on the Navier-Stokes equation. Okay, its origin is actually from the Navier-Stokes equation. So here you will deal with variable properties like pressures, velocity, area, mass, etc. Okay. For example, you know that nowadays when this is an F1 car, right? So which is actually cruising at a very high speed. Now you know that the airflow or the fluid flow is now going to hinder or obstruct the movement of this car. But in order to have minimal effect, there might be some aerodynamic cuts. You might see in your car bodies also where aerodynamic cuts are there. So the air which actually tries to try to approach this car body will surpass it without doing much disturbances. Okay. Whereas in olden days we don't have this type of analysis itself. So if you drive your car, say for example some 80 km per hour or 90 km per hour, you might feel that your car has been pulled like this or this. Now, this is not going to happen in most of the new modern cars because of the aerodynamic cuts present, and that is because of the finite volume method analysis. Okay, so here the inputs will be mostly of velocity, pressure, mass flow rate, temperature. And outputs will be same like you might study about the velocity, pressure, temperature distribution. And this is a basic for your aerodynamic part, which is lift and drag coefficient. Okay. Now there is one more method, which is a final method, which is called finite difference method. So finite element and finite difference method share many common things. In general, finite difference method is described as a way to solve a differential equation. So what are all the different numerical methods which are available for you to solve? Then that falls under the category of finite difference method. So that's what I said, that it is just a mathematical technique. And it is generally used in combination with the boundary element method or finite volume method to solve coupled problems of thermal and CFD. So I'll show you an example for that. So let's say you can take an airplane wing structure. So my aim is to find out the stress distribution in this airplane structure. But the problem is I don't have any force as input. If there is force as input, then immediately I can do the stress analysis using finite element method. So now I can't do so because I have been given with the flow of air, mass flow rate in kg per second. Okay. So now what I can do is I can do the analysis on finite volume method and try to find out the output parameters like pressure and force. Now, after finding out the force, then I can take this model and couple it with finite element method where I can analyze the stress distribution. So, which is nothing but a coupled problem. I can't directly go and find out the stress. Instead, I'm just finding out some other output parameter relevant to stress, which is pressure or force. And then I'll convert this into finite element method. For this coupled problems, you will generally use the finite difference method as a mathematical technique. Is this clear? Hello? Shanti, it is clear, right?
Yes, sir, it's clear.
Yeah. So now computer data engineering, it is a broad usage of computer software to aid in the engineering analysis tasks. Okay. So it mostly includes the finite element analysis with computational fluid dynamics and multi-body dynamics and how to optimize the things. Okay. See, optimization is a crucial thing for any CAE engineer to decide that how far the modifications has to be done and how to actually optimize the different parameters which are actually involved in the design of the entire component. So CAE retrieves the description and geometry from the CAD database. As I already said, that CAD is the one department which has to give the component to the CAE. Okay, so it is used in almost every industry such as aerospace, automobile manufacturing, and CAE depends on CAD. Okay, just a second, Ashanti, I'll come. Just a second. Yeah, sorry, I just got a call. So now I'll show you what is the difference between CAD and CAE, which we have already seen. So CAD is all about the creation and generation of the 3D model. That's all. Nothing else they will do. Okay. CAE is about the testing the characteristics of the material, strength, fatigue, and etc. using the engineering method, usually the finite element method and all the numerical other techniques. Okay. Say for example, let us take a bridge construction. So this also falls under the same category. Even though it is of the scope of civil engineers, but still they will also use some analysis software to do the same. So the procedure is same. So basically they will create a model like this 3D model, and then this CAD model geometry will be sent to the CAE department, where there will be a department for meshing. They will start dividing this into several small elements, and then after meshing they will try to apply the loading conditions, where the exact load and how much load and what is the end boundary conditions, everything. Then they will subject and try to solve for the stress and strains, and they will study the answer, something like this. So this is what happens. Okay. Now we'll do something like this. See, now we are going to see what is finite element analysis and finite element method. Is both the method is both are same or different? Then what is
Sir, excuse
discretization?
me.
Yeah,
Can I ask the question?
yeah, tell me.
So how exactly do people develop the CAD model? Are they given certain, um, uh, how exactly is the CAD model developed?
See, CAD model, they'll draw using the using the softwares like SolidWorks. Have you heard about SolidWorks, Creo,
Yes.
CATIA,
Okay.
NXCAD? So these are all the softwares that they will use to create the model. The thing is, after
So,
creating a model, yeah, tell me.
so how exactly, like the dimensions for the product,
Yeah, the
does the
dimensions
client
for the
give?
product would be initially given to them with some views, like orthographic views will be given. Okay. The dimensions will be
Okay.
generally fixed by the computer aided engineering department. So without dimensions, this CAD model department cannot even touch the model. So they will be given with
Right. Okay.
certain views and dimensions.
Right. Okay. Okay. Okay.
And then they will
So,
draw and keep this file in universal graphics standard format. See, each and everything has a file extension format also. Like for example, .pdf is a format, right? But using this PDF
right.
format,
Yes.
you cannot export that file to this computer-aided engineering softwares like ANSA, ANSYS, and try to do the analysis. This is not possible. Similarly, there is something called as
Okay.
.part format, .prt. That also doesn't work.
Okay.
So the only universal graphic standard which you have to follow is IGES or STEP. These are all the two universally accepted graphic standard for any softwares, whether it is CAD or CAE. So what they'll do is they'll try to model and keep the file in this format. While saving itself, it will give you the option that whether you have to file in which you want this file in which format. At that time, they have to choose either one of these, IGS or STEP. Now this can be exported to this software, and then we can do the analysis.
Okay.
Okay.
So initially, the design has to start with the CA department.
Yeah.
Whenever
Basically, it
new
is
has
they
to
will
be
give the rough dimensions and everything, and then they will try to check for the stress and other output parameters. If it is not that, then again they will redo the dimension and then give it back to CAD department. So CAD department will again draw and do the modification and send it back here. Now this time they will check for the output parameters and see whether within the limit or not, and then correctively they will give the information to the CAM.
okay. Okay. Thank you, sir.
Thank you. Now, the thing is, we are now going to see what is discretization of the problem. Okay, so which is very, very important because it is a first thing which you are actually been familiar with this because you are not included finite element method as one of the subject in your UG. So why do we carry out meshing, and what is the meaning of degrees of freedom, and what are all the different element shape characteristics, and 10 questions you should be able to answer before even getting on to any problem. So finite element method. So I'll share this PDF with you so that you can also have some notes with your hand, which will help you a lot. Okay, now I'm going to explain. So let's take, for example, this sheet metal. So I'll consider this sheet metal as 2D. Why? Because when you compare this dimension with this dimension and this dimension, thickness is almost negligible. So I can consider this as 2D. Okay, so compared to length and breadth, the thickness is negligible. So I'll consider this as 2D. Now, see, if you take the actual sheet metal part, top face or bottom face, whatever, it has infinite number of calculative points, which means it has infinite atoms or molecules. You can imagine in that way. Now it is impossible for me to do the calculation at this point, and this point. Let's say, for example, our aim is to find out the stress for this particular 2D sheet metal. Then I'll not be able to do the stress for infinite number of points, right? So that's why I have to convert this into finite number of points. Okay, that is called as nodes. Now, how will you arrive at that nodes? You require something called as shape. So the shapes which has been created using the nodes is called as elements. Now I'll say, for example, let's assume that this is some 100 cross 100, 100 mm into 100 mm. Now you will divide that into perfect squares of different sizes. Now this shape is nothing but the element. I'll hatch and show. This is element. But this element has been formed using 4 corner points. Those are called as nodes. Now, after doing this, I can count this. I have finite number of nodes, but in this case, it is infinite. So generally, all the bodies will be infinite, where I can't directly subject it to a numerical method, where I need to calculate the output parameters like stresses and strains at different locations, infinite locations. It is not possible. So I need some finite quantity. So for that, I'm actually doing some shape analysis or shape characteristics, where I'll end up with some elements, and the corners of the elements are the points which form the shape is called as nodes. At these nodal points, I'll evaluate the stress, strain, and everything for the output parameters. Then you might ask a question that, if you are evaluating at this node, what is the stress and what is the stress at this point, then what happens between the element? So that's what is very important. See, at the nodal points, we will exactly evaluate what is the stress. But between the nodes, which is called as the element, we will approximate the results. And that is called as interpolation. Do you know the meaning of interpolation in maths?
Yes, I think so.
Yeah. Say,
If you
for
have the
example,
value.
let's say, for example, you might have read about, you might be familiar with the enthalpy, right? Enthalpy in thermodynamics.
Enthalpy?
Yeah, enthalpy.
Yes.
Okay,
Yes,
let's say
thermodynamics.
that I'm using a steam table where I'm finding out the value of the enthalpy. For 300 degrees Celsius, they might have given some value, and for 350
Okay.
degrees Celsius, they might have given some value. But what if
Okay.
suppose I want it for 330 degrees Celsius? Then I will use these two values to find out this one, right? That is a kind of
Yes.
approximation. Then that is called interpolation. So mathematically,
Right.
I have a start point and end point for a curve, but I want to find out the trace point of the middle points. Then that is interpolation.
Right.
So you have to
Okay.
keep one thing in mind, that exactly at the nodes you are evaluating the output parameters, but between the nodes you are approximating the results. So as far as meshing is considered, meshing and discretization both are one and the same. You are dividing the given geometry into several smaller unit or element sizes. So as far as calculation point and accuracy is considered, go for more number of nodes, because at nodes you are exactly evaluating, but reduce the number of elements.
Mhm.
But you might wonder that, sir, both nodes and elements are directly proportional. No, that is not the case. In the following lectures, you will come to know that you can create more number of nodes, but reduce the number of elements. I'll tell you how to do that. Okay, but now you have to remember that results are calculated at the nodal points exactly, but it is interpolated between the elements. Okay.
Right. Okay.
So this you have to remember. Then finite element analysis and finite element method is that both are different. Actually, both are same only. But finite element analysis is a word which has been most popular in industries, while finite element method is a common phrase which has been used under the universities. Educational universities will use the word finite
Okay.
element method. Both are one and the same. So advantages is you
Okay.
have a better visualization of the real-time application. It will actually reduce the design cycle time. Okay, manually if you try to
Mhm.
do the design, then it will take a huge amount of time. Then it also decreases the number of prototypes because we are not following the experimental method. It actually
Right.
cuts down the testing cost also, and optimum design can be achieved at
Mhm.
a much faster rate. So these are all the different
Okay.
things which are available for finite element method. Then the discretization is been given in detail here, where I have already explained. Okay, so discretization and meshing are one and the same. Dividing the given infinite number of points in a space into known shape using nodes and elements is called as discretization. Okay. Then
Okay.
basically for all mechanical, you have these three functionalities: mass element, spring element, and damper element. Okay, so the function of mass element,
Mhm.
it has actually been associated with the movement, acceleration, deceleration, inertia, and everything. Spring, that it is
Mhm.
used for shock absorbing thing, right? So it is mainly
Yeah.
used to absorb some energy. And the damper also reduces the vibration because of by external means. So these are all the three basic fundamental units which any mathematical modeling will actually get subjected to. Okay. So then comes the degrees of freedom. So I'll start from the degrees of freedom in the next class tomorrow. Okay. So
Okay.
for two classes, we'll be going on to the theory part. Then we'll be entering into the answer. And you tell me some timing in the Indian Standard Time, anything after 8 p.m. for your ANSA
Okay.
software to be installed in your computer. You can actually send your mail ID to me, so that we'll send you a file. Please do download that and keep it ready and connect it through any
Okay.
disk, so that we'll be able to operate your remote computer and install it for you.
Okay. Okay, sir.
Okay.
So today at 8:30 then?
Yeah, 8:30 is fine. But you send your mail ID
I'll
first,
send
okay?
the email.
Yeah, yeah,
Yes,
yeah.
I'll send okay if I WhatsApp it?
Yeah, yeah, sure.
Okay.
Sure. So I'll share this video. This video has now been recorded with all your voice and my voice and this entire PPT and everything. Okay. So now I'll share this
Okay, right.
video also. You just watch it after half an hour, because it tries some time for uploading. Okay. It takes some time for uploading.
Right, okay.